Ever stop to think about what makes your phone buzz in your pocket? Or how an electric car can just go with so much power? Well, the answer is this incredible invisible force. It's a secret link, really, between two of the biggest players in the universe, electricity and magnetism. And today, we're going to pull back the curtain on that secret.
So, what could a simple compass and a plain old copper wire possibly have in common? I mean, they seem totally unrelated, right? One points you north, the other, well, it just carries electricity. But believe it or not, they share this super deep connection, a secret that took us until the 19th century to finally figure out.
Okay, so let's set the scene. It's 1820. You've got this Danish scientist, Hans Christian Oersted, and he's in the middle of a lecture. He's just showing his students how an electric current can heat up a wire. Pretty standard stuff. But then, something totally unexpected happens. He flips a switch to turn on the current, and a compass needle sitting on a table nearby, it just jumps. It twitches and points right at the wire. It was a total accident. You know, one of those moments of pure scientific luck that literally changed everything.
And look, this wasn't just some small, neat little discovery. No, this was a massive deal, a complete paradigm shift. Before this moment, everybody thought electricity and magnetism were two totally separate things. But Oersted's little accident, it proved they were actually two sides of the same coin. They're part of one single force, electromagnetism. And that discovery, it's the reason we have electric motors, generators. You could even say it's the grandfather of the internet.
All right, so how do we get from a twitching compass needle to, everything in our modern world? To really get it, we need to take a step back and look at the basics. We've got to understand this invisible force that's all around any magnet. We're talking about the magnetic field.
Check this out. This is literally what a magnetic field looks like when we make it visible. You just sprinkle some iron filings around a magnet, and they don't land in a random pile. No way. They line up perfectly, tracing out these beautiful flowing lines. It's like they're revealing the magnet's invisible force field for us to see.
So a good way to think about it is it's kind of like a spider's web. The magnet is the spider at the center, and this magnetic field is its invisible web stretching out all around it. And anything that wanders into that web is going to feel the spider's influence, right? Same idea here. Anything that enters the magnetic field can feel the magnet's force.
Now, these lines, they follow a few simple rules. First, they always flow out of the North Pole and loop around back into the South Pole. Think of it like a one-way street system. And here's the key. See how some lines are bunched up close together? That's where the field is super strong. Where they're spread far apart, it's much weaker. And the one rule they absolutely never break, two field lines will never, ever cross each other. It's this perfectly ordered invisible map of force.
Okay, so we've got a handle on what a magnetic field is. Now let's circle back to Oersted's big moment and see exactly how a simple electric current can create one of these magnetic fields all on its own, right out of thin air. So when you send an electric current flowing through a straight piece of wire, something pretty amazing happens. The wire generates its own magnetic field. And it's not random. It swirls around the wire in these perfect circles, almost like ripples spreading out in a pond.
And figuring out how strong this field is, it's actually super simple. It comes down to two things. First, the amount of current. The more juice you pump through that wire, the stronger the magnetic field gets. And second, distance. Just like feeling the heat from a campfire, the further you get from the wire, the weaker the field becomes. Makes sense, right?
All right, so we know the field is made of circles, but which way are those circles spinning? Are they going clockwise, counterclockwise? How do we know? Well, luckily, you don't need some crazy equation to figure it out. All you need is your right hand. There's a super handy trick called the right hand thumb rule. You can actually do this right now. Go ahead, take your right hand. Imagine you're grabbing that wire. Now point your thumb in the same direction the current is flowing. Got it? Okay, now look at your fingers. The direction that your fingers are curling, that's the direction of the magnetic field. See? It's that simple.
So, a straight wire gives us these nice circular fields. That's cool. But what if we need something stronger, something more focused? Well, the answer is surprisingly simple. You just change the shape of the wire. So watch what happens when we take that straight wire and just bend it into a single loop. Suddenly, inside that loop, all those little circular field lines start to add up. They combine and reinforce each other, creating a way stronger, more concentrated field right there in the middle. You can see how all the lines are now pointing the same way inside the loop. It's a huge boost. Okay, so if one loop makes the field stronger,
what happens if we use 100 loops, or even 1,000? Well, that's exactly the idea behind something called a solenoid. Just think of it like a slinky, but made of insulated copper wire. It's just a whole bunch of those loops, all coiled up together. And this is where it gets really cool. When you pass a current through that solenoid, the magnetic field it creates looks exactly like the field from a regular old bar magnet. Seriously, one end becomes a north pole, the other becomes a south pole, and the field lines loop around from one end to the other, just like what we saw with the iron filings at the beginning. This is an absolute game changer. Why? Because the field inside that coil is not only incredibly strong, it's also really uniform and predictable. So just by running electricity through a coil of wire, we've made a magnet that we can turn on and off whenever we want, just by flipping a switch. This is the basic idea behind all powerful electromagnets, from the massive ones in scrapyards that lift cars, all the way to the super precise ones used in MRI machines and particle accelerators. All right, so we've established that electricity can create a magnet. That's huge. But believe it or not, that's only half the story. The other, equally amazing half is what happens when you take a wire that's already carrying a current and you place it inside another magnetic field. This is where things get really interesting. Yeah, when you put that current-carrying wire into a magnetic field, the two fields interact. They don't just pass through each other. They actually push and pull on one another, and the result is a real physical force. The wire actually moves. And you guessed it, just like before, there's another simple hand trick to figure out which way that force is going to push the wire. We used our right hand before, so this time we're going to use our left. It's called Fleming's left-hand rule. Let's try this one too. Take your left hand. Now stretch out your thumb, your forefinger, and your middle finger so they're all pointing at right angles to each other, kind of like a 3D axis. Okay, so your F4 finger points in the direction of the magnetic field, your middle finger points in the direction of the current, and your thumb points in the direction of the thrust or the force. It points right where the wire is going to move. Pretty neat, huh? And again, this is so much more than just a cool physics trick. This principle, this force, is literally the engine that drives our modern world. It's the secret behind every electric motor. It's what makes the speakers in your headphones work, what makes your phone vibrate. It's the reason an electric car has that insane acceleration. It all comes down to this fundamental force of electromagnetism. So let's recap. We've seen how electricity can create magnetism, and we've seen how that combination can create motion. It's a pretty powerful chain of events. But it makes you wonder, doesn't it? What about going the other way? Could you use a magnet and motion to create electricity? Well, the answer to that question sparked a whole other revolution, one that literally lit up the entire planet. But that's a story for another explainer